Hello and welcome to the Significant Figures video. If you haven't already, please download and take a look at the Significant Figures activity in Canvas. These videos are designed to match with the activities, and these videos are going to explain how to solve the problems in the activities. Well, moving on to our topic at hand, significant figures. If you've taken a chemistry class before, you're probably familiar with them and maybe even have some sort of bad memories of them. They're a bit tricky, but thankfully we'll be working on them all quarter long. So we have to begin our discussion of significant figures by talking about measured versus exact numbers. And so we have a couple different types of exact numbers. We have counted items is one type. And so counted items are going to be, just what the name implies, things that we count. And crazy as this might sound, these are actually exact numbers. So for instance, 8 donuts. If we have 8 donuts, there's exactly 8 donuts. There's not 7.5 donuts or 8.23 donuts. It's exactly 8 donuts. And examples that we might see in medicine would be, maybe you give a patient 2 tablets of a medication. That'd be exactly 2 tablets. So those are counted objects. And these pop up in chemistry classes. Some examples would be, for instance, particles in atoms are oftentimes exact. So an atom might have 13 electrons or 6 protons. Those are actually exact numbers. And similarly, we see exact numbers in balanced chemical equations as the coefficients, and we'll be talking more about those later in the quarter. So they do pop up. And our other type of exact numbers are going to be definitions where we compare units in the same measurement system. So for example, in the metric system, any of these comparisons we see within the metric system are going to be exact. So they give some examples here, but for instance, 1 kilometer equals exactly 1,000 meters. There's no error in that comparison. The definition of a kilometer is it's exactly 1,000 meters. And here in the US system, we again see exact relationships. So for instance, 1 mile is defined as exactly 5,280 feet. And so although we have some kind of weird numbers in the US system, those are also exact numbers, those comparisons within the system, because they are defined quantities. I will mention, however, if we go system to system, these are going to be measured. There's going to be some error involved in these comparisons. And an important thing to note about exact numbers is that they do not affect the number of Sig Figs in our calculated answer. More on this later, but essentially what this means is because there's no error in exact numbers, they aren't going to create error in our answer. So moving on to our other type of number, we have measured numbers. And an important thing to know about measured numbers is they are not exact. So these measured numbers are going to be measured using some kind of measurement device, some kind of machine. And these measurement devices or measurement machines, they're never perfect, so there's always some error associated with them. So whether you be using a really crude tool like an hourglass or a really precise tool like an atomic clock to measure time, there's always some error associated with that. And some tools we'll be using in this class in order to measure things are going to be analytical balances or scales to measure mass, graduated cylinders to measure volume, clocks or stopwatches to measure time, and rulers. So we're actually going to be taking a lot of measurements in this class, but also you're going to want to be able to recognize if a number you're given is exact or measured. And let's take a shot at doing that. We have 3 different quantities here, and we're asked to determine if they're exact or measured. The first one is 3 coins. Well, this is an example of counted objects. So this one would be exact. I'm putting E for exact. So if we have 3 coins in our pocket, that's exactly 3 coins. There's no error associated with that. And then right here, the diameter of a circle is 7.902 centimeters. Well, this one's going to be measured. This diameter of the circle, we'd somehow have to measure the circle in order to obtain that quantity. So there'd be some error associated with it. Then finally, 60 minutes equals 1 hour. Well, this is going to be exact. This is an example of a defined relationship. An hour is defined as containing exactly 60 minutes. So we have counted objects, defined relationships, and measured quantities represented here. Let's see how we did. Excellent, we got this problem correct. I'd like you to now pause the video and please complete question number 1. Once you've finished question 1, please come back and restart the video. Welcome back. Let's move on. Let's talk about, if we're given a number, how we recognize how many significant figures are present in that number. So we have some simple rules here to try and determine how many significant figures are in each number we're given. And our first rule is that all non-zero digits in a given number will be significant. If we look at this number 234 right here, we have 3 digits. All of them are non-zero digits, meaning they're all significant. So our first number right here would have 3 sig figs, and I've underlined our 3 sig figs in that first number. If you haven't figured it out, sig figs is short for significant figures. Now zeros are tricky. Zeros can sometimes be significant and sometimes they're insignificant. So zeros are going to be significant when they're between non-zero numbers. So these numbers in this value 50,071, these are actually significant. So we have 3 non-zero digits, all of which are significant, and then 2 what we call sandwich zeros sometimes, meaning we have a total of 5 significant figures here. And the other time zeros are significant is when they're at the end of a decimal number. In other words, to the right of non-zero digits and numbers with a decimal point. So this particular number actually has 4 significant figures in it, and I've underlined them here. So we have a non-zero digit, and those are always significant, the 5 right here. But then we have 3 zeros to the right of that 5 and a number with a decimal point in it. Therefore, this number has 4 significant figures. Now, zeros are sometimes not significant. Sometimes they're there to show us the magnitude of a number, and they aren't actually significant. So in the example of 25,000, so we have zeros to the right of non-zero digits and a number without a decimal point. And so the 2 and the 5 are non-zero, they're significant, but the zeros are not. So we actually have 2 sig figs right here. So what this implies is this is a pretty poor measurement. The fewer sig figs we have in a number, the lower quality of the measurement, and so this means this is a pretty poor measurement, and someone probably rounded it. The zeros here just to show us the magnitude of the number. Over here we have the other place where zeros are not significant, to the left of non-zero digits and a number with a decimal point. So this one actually has 3 sig figs in it, so I've underlined them, these 3 non-zero digits right here. The zeros out in front are not actually part of the number, they're just there to show us magnitude, so they are not significant. So let's take a look at these values right here and try and figure them out. How many significant figures are in the following? Well, in this first one right here, we have 3 non-zero digits, and then we have a 0 to the right of non-zero digits and a number without a decimal point. So this one actually only has 3 significant figures in it. Moving on right here, 0.012. This one actually has 2 significant figures. So these zeros again are not significant, but this time because they're to the left of non-zero digits in a number with a decimal point. So we have just 2 for this value. 8.20, well, we have 2 non-zero digits, but our 0 is significant in this case because we have a 0 to the right of non-zero digits and a number with a decimal point. So we have 3 significant figures here. And then finally, this number in scientific notation, we can just use our normal rules here. So we actually have 4 significant figures here. So we have 2 non-zero digits, but also both our zeros are significant. We have a sandwich 0 right here, and then we also have a 0 to the right of non-zero digits and a number with a decimal point. So this one has 4 sig figs. So let's see how we did. Fantastic, we got them right. So you should now pause the video and please complete question number 2. Once you've finished question number 2, please report back and start watching the video again. Welcome back. We mentioned previously that the number of sig figs in a value gives some indication of the measurement quality, and that measurement tools vary a bit in their quality. So one of the things that we'll be studying in lab, if you haven't completed lab already, is the idea that for analog machines, we want to record 1 digit past the markings. So right here, for example, we're using a pretty low quality ruler. It's just marked the nearest centimeter. And we want to estimate 1 digit beyond that. So we end up with a value here of 4.5 for the length of our stick right here, because it's about halfway between that 4 and the 5. So we go 1 digit past the markings, 4.5. But if we use a higher quality ruler, one marked to the nearest tenth of a centimeter, we can actually estimate to the hundredths place, and we see that our value is somewhere about halfway between 4.5 and 4.6, meaning we have a value of 4.55. So again, we go one place past the marking. So if we're marked to the tenths, we go to the hundredths place. And so we now have 3 sig figs. So this is a higher quality measurement, and we report more sig figs. So sig figs can give us an idea of the quality of our measurement. Down here, we're back to a low quality measurement machine. We have just marked the nearest centimeter, and we can see the length of our stick is almost exactly on that 3 centimeter mark. So we're going to go one digit beyond that. We're going to estimate to the tenths place, 3.0. So notice that we don't just write 3, we actually know one more digit than that. We write 3.0, so that's 2 sig figs. And if it seems confusing, we'll be practicing this in the first lab, so hopefully it'll make a little more sense after that. So one of the tricky things you'll be asked to do is use significant figures in calculations, and this can be confusing. Well, we'll try and simplify it by talking about some rules, but you should be aware that your calculator is typically going to give you the wrong number of sig figs, and sometimes you'll have to round it to fewer digits than the calculator displays. Other times you'll actually have to add back in zeros that it's rounded away. So just be aware, whatever answer your calculator spits out, you're probably going to have to modify in order to get full credit. So let's talk about our rules here. Well, let's begin with rounding off. So if the first digit being dropped, so the first digit we're not going to include in our answer, is 4 or less, then we're going to simply drop the trailing end, or we might say that we round the number down. If the first digit to be dropped is 5 or greater, then we're going to round up. Now let's talk about how to handle these calculations in a math problem. So we have one set of rules we use when multiplying and dividing. And the rule is pretty simple. What it states is our answer can't have more sig figs than our measured number with fewest sig figs in our calculation. The way I like to think about this is our answer can't be higher quality than the lowest quality number in our calculations. So for example, here we're multiplying 110.5, which has 4 sig figs. That 0 is sandwiched, so it counts as significant, by 0.048, which has just 2 sig figs. This is a lower quality value. And that means our answer quality is limited. If you punch this into your calculator, though, it's going to spit out something like 5.304. The problem here is that's written to 4 sig figs, but we can't actually know our answer to 4 sig figs because this value right here is too low quality. It's going to limit our answer quality. And therefore we can only know our answer to 2 sig figs. We have to round this to 5.3. So the first digit we're dropping is that 0, so we round down to 5.3. Now we have a somewhat similar rule for adding and subtracting, but it's based on decimal places. So when adding or subtracting, our answer can't have more decimal places than the measured number in our calculation with fewest decimal places. Again, it's another flavor of our answer can't be higher quality than the lowest quality number in our calculation. So our first number, 25.2, is known to 1 decimal place. In other words, we just know the tenths digit. And in this second number right here that we're adding, we actually know the hundredths digit. So we know both the tenths and the hundredths. It's known to 2 decimal places. If you punch this into your calculator, it's going to spit out this answer of 26.54. Unfortunately, we don't actually know what the real value for that 4 right there is because we don't know this digit right here in our first value. In other words, we've written our answer to more digits than we actually know, so we have to round this. And so the first digit we're dropping is the 4. It's 4 or lower, so we round down to 26.5. So I'd like you to now pause the video and please complete questions 3 through 5. Save question number 6 for after the next video lesson. It'll be some good practice for the material from the next video activity. All right, thank you. Bye.